Welcome, everybody. My name is Tim Kaxiras. I'm the chair of the physics department, and it is my distinct honor and great pleasure to introduce to you this event and to welcome the lecturer for our Lee lecture, historical Lee lecture today, Professor Stephen CHU. But this event is more than just a lecture. It also includes a couple of other announcements, which I'm very happy to make. At the Lee lecture, we also announce the winners of two very prestigious awards in our department and at the university, the Gertrude and Morris Goldhaber Prize in Physics and also the Merit Fellowships. So let me start with the announcement of these awards. So the Gertrude and Morris Goldhaber Prize in Physics is awarded annually to an outstanding theoretical and one outstanding experimental graduate student. This year, the pool of qualified students was exceptionally strong, and after much discussion at the faculty meeting, we decided to award 4 prizes, 2 to theory students and 2 to experimentalists. So the awardees in theory are Rodrigo Araiza Bravo, who works in atomic, molecular, and optical physics, and Maine Christos, who works in condensed matter theory. Are they here? And the awardees in experimental physics are Sefer Ebadi, who works also in atomic, molecular, and optical physics, and Barbara Skriprek, who works in high-energy experimental physics. So please give them a So I also want to acknowledge the winners of the Harvard Merit Fellowship. This is a different award, and it has to do with students who have passed their qualifying exams and have an approved dissertation project. So the winners of the Merit Fellowship are chosen by the Graduate School of Arts and Sciences from among all nominations from all departments in the university. And the award allows students to focus their time on research and writing. This year, 2 physics students were awarded a Merit Fellowship, and they are Erin Crowley and Katie Fraser. So let's give them a big hand also. Okay, so these were the announcements of the awards. By the way, we have a special ceremony next week on May 1st, where we celebrate the award winners for all sorts of awards that we have in the department, including the ones that I just mentioned. I hope you can make it to that, and we'll say a few more things about what each awardee has done. So now a little bit about today's lecture. So the David M. Lee Historical Lecture in Physics is sponsored by the Marvin and Annette Lee Fund. The David M. Lee is a professor emeritus of physics at Cornell University and distinguished professor of physics at Texas A&M University. He shared the 1996 Nobel Prize in Physics with Robert Richardson and Douglas Osheroff for their discovery of superfluidity in helium-3. Unfortunately, Professor Lee cannot attend today's lecture, but we are very happy that his son, Jim Lee, and one of his grandsons, Daniel Lee, are with us today. They're sitting over there. Thank you for joining us. And as I already mentioned, the lecturer for the historical Lee lecture is Professor Stephen CHU. But I have asked my colleague, Professor Peter Gallison, who is the Joseph Pellegrino University professor and the faculty director of the collection of historical scientific instruments, to introduce the speaker. Peter.
Thank you. It's an enormous pleasure professionally and personally to welcome Steve CHU back to Harvard. He did a first miraculous transformation in changing from being a theorist to an experimentalist in 76, 78 as a postdoc, I believe, and then went on to do an amazing and beautiful set of experiments around atomic fountain clock, around getting polarization gradients and using them to cool. He used lasers and matter in many different ways to understand the way atoms could interact in their fundamental quantum mechanical lives. And he even, perhaps most dramatically, attached micron scale polystyrene spheres to DNA, which seems just a miracle when one thinks about it, and which led to a whole world of new ways of manipulating these vital molecules. Somehow, in the midst of this, which garnered him the shared Nobel Prize of 1997 on cooling and manipulating atoms, he found increasingly important these questions of global climate change, global warming, and energy in all of its manifestations. He became head of Lawrence Berkeley Laboratory in 2004, was tapped to be Secretary of Energy in 2009, and then, since no good deed goes unpunished, in 2010, the Deepwater Horizon platform blew up and created one of the greatest environmental disasters in recent decades. And Steve took the helm, helped direct those efforts around trying to close that well, and played a role that only somebody with his breadth of knowledge, his deep interest in environment and in the climate could muster, and helped resolve one of the real tragedies of the environment and of the Gulf of Mexico in particular. It's an enormous pleasure to welcome him back to Harvard. I think maybe the last time was when you were Secretary of Energy, or have you been back since? But I do remember.
I've been back at least once or twice.
Okay. But he's a great physicist with wide interests. He's somebody who's a pleasure to talk to. When I was a young professor at Stanford in the physics department, he came in 1987, I think, and became a good friend and somebody with whom it was a great pleasure to talk about all kinds of physics and things beyond physics. It's with pleasure and delight that I welcome Steve CHU.
Thank you, Peter. I'm delighted to give this talk. And the theme of the talk, I hope I can impress upon you, is that once you understand things in a very simple freshman, sophomore physics way, you can actually, and become so intuitive and obvious, you can maybe do things, you can make a next step. And so those are some of the things I want to share with you. Just trying to think here. Anyway, and it's an embarrassment of how simple some of this stuff was, and it's also, I want to convey at least some of the collective effect of science and how it works. So let me start with this. I'm looking at the circle. I'm not sure why that circle's there, but it doesn't matter. Peter got mostly right. I started graduate school. I was a math major and physics major. Did well in my qualifying exams at Berkeley. And so my advisor, Gene Cummins, thought I should do some theory. And so he assigned me on an astrophysical theory project, binary protostar formation. But I actually would sneak in the lab and do toy experiments. And finally I said, Gene, look, I want to work on lasers. So, and why? Because dye lasers were invented, this was in the early 70s, 1971. Started graduate school in 70, passed the clause 71, and was off. I thought, but Gene said, well, I don't know anything about dye lasers. Don't worry, I'll learn about dye lasers. We're just going to do an experiment with dye lasers. So I said, sure. And so we eventually landed on what we thought was a great project. It was an experiment proposed by the Bouchias that using circularly polarized light, you can excite a highly forbidden magnetic dipole transition, but because weak interactions violate parity, what would be a parity violating reaction would allow weakly parity change due to the weak interactions. And so it would be an asymmetry of a part in 1,000 of a transition that was so weak, nothing that weak had even been induced before. And so that's what my thesis was. After 3.5 years doing that, it wasn't look like it was, I said, my advisor, I said, I've suffered enough. I'll make you a deal. Give me a PhD. I'll stay and finish the experiment as a postdoc. He said, sure, because then I could get a postdoctoral fellowship. So it was better for him. That's me when I was younger on a laser that I built. I was actually for a while building flash lamps as well, but I stopped doing that. And so anyway, and so this is an upgraded version for whatever reason yes. So this is the room next to the room where we had the chamber. And so we punched a hole in the wall and it goes through the mouth of that clown. For whatever reason, in the spring of 1978, they made me assistant professor. And they said, here's a bunch of start money, you can start your group. But, you've been here as a graduate student and postdoc working in the same experiment for 8 years, and really 7 on this experiment. And so we said, we want you to be a faculty member, the job's yours, but you can also take a leave of absence. So I said, took the job, I spent the start money on this stuff, with a beginning graduate student who would be my first graduate student. Her name's Persis Drell. And so off we went and built this stuff. And so that's what happened. Oops, why is this not? Okay. And I got to say, when they hired me, I didn't know much about physics, but I knew how to build really good lasers. So off I went to Bell Labs with the idea of staying there 2 years. So what did I do at Bell Labs? I worked on Anderson localization with high Gibbs Sam McCall to test localization. And we found that the thing that Phil Anderson said was the only clear example of Anderson localization turned out to not be true. So it was a null result. I worked on exciton mobility, Anderson, things like that. Pulse propagation, I discovered quite by accident that if you send a pulse to an absorbing medium, due to Kramer's Carter relationships, the pulse can actually, the peak of the pulse can be shown analytically if it's a Gaussian, comes out of Gaussian, but it's attenuated. But you can get it so the peak of the pulse emerges before the peak of the pulse enters the sample. So think of this Gaussian going through the sample and you're squishing the back end of the pulse and it looks like it goes forward. And so it can go at faster than the speed of light, infinity, negative. So the peak emerges before the peak enters. This was rediscovered by others, but anyway, as well, but it was classical A&M. And then I did some positronium spectroscopy with Alan Mills, which was, it got some headlines, but it actually didn't lead to anything new. So far at Bell Labs, a total failure. And then in 1983, I was recruited by Chuck Schenck to go from Murray Hill with an A to Homedale to head a newly formed quantum electronics research department. And it's there that I met Art Ashkin. I had seen him when I was interviewing, but then he's there in the same department as, same laboratory as me, Chuck Schenck's laboratory. And he had learned from a professor at the University of Toronto in the mid-1960s that if this professor discovered if you have a laser beam, and he noticed these little dust particles would be entrained in the laser beam. And they wouldn't, he's just looking at it. And so Ashkin had a even more powerful laser instead of a Heaney laser. He had an argon laser. In those days, they had glass tubes. You can lift the lid off, foil the interlocks, and you can peek in, and you see this, he said, you can see this dust running back and forth, clearly trapped. And so Rawson actually identified the so-called dipole force. I'll explain a little bit about to you. And Ashkin also independently discovered what the mechanism was a little later, but nevertheless. he starts going to town and begins to say, what can you do with this? So in a paper in 1970, he did an amazing series of experiments. So this paper has got like 6,000 or 7,000 references. So in this first diagram, he took a laser beam, and the dipole force would entrain it here. And again, I'll explain in a moment how it works, but a particle would be trapped here and would be pushed against this side of the plate, and the force would keep it localized in the orthogonal direction. Of course, the glass plate would keep it localized in that direction. So I said, well, maybe I want to localize it in free water solution. So I focus here and I focus here. And the idea is if this particle moved over here, it would see more scatter. It would scatter more photons from this and push over here. And if the particle moved over here, it would see more photons and push over here. And this strong electric field would be polarizing the particle, and it wanted to trap the particle in a field maximum, and so it would be trapped here. And so he did this experiment in 1970. He looked at it, and if you have bigger particles, you can actually think of it as a lens. Okay? That was in 1970. In 71, he levitated a particle. So a particle now in a vacuum, levitated, pushing up against the particle, against gravity, along this dimension, the particle's attracted to the strongest laser field, okay? That was 71, and then he started getting interested in atoms, and he published a paper in 1978 that's had the same sort of configuration as this one in water, but he said, okay, why don't we try to do this in vacuum? You have an atomic beam coming this way, and the scattering force, if the atoms are over here, the scattering force would push it this way. If the atom was over here, the scattering force pushes this way, and he hoped the dipole force would keep it like that. So he published this paper in 78, but by about 1978, everything closed down at Bell Labs experimentally with atoms. Because they weren't really making progress. They showed that the dipole force on an atom beam actually could take a collimated beam and focus it a little or defocus it. They pushed the scattering force this way, pushed it over, it all worked. But that's a long ways, but you have a well-collimated beam, the effective velocity spread is very small in this direction. So it's going very fast. So how does this thing really work, and what was really the object of this? So if you want to hold on to something, if you cartoon of look at the atoms of your finger and the atoms of the object, you're distorting the electric fields on your finger and the object, and there's a polarization of those molecules, and you have a little resistive force, so that means you can hold on to something. And so, okay, so here's something you can also work, and that's how you hold on to something, but you have to touch it. Now, if you want to hold on to something at a distance, if you take a charged rod and you have a neutral particle like a piece of paper, the electric field on average makes the opposite charges attracted towards the rod, and the positive charges on average are pushed, the center mass of those charges are pushed away. So you induce a dipole, but because the field is stronger here than here, the attractive force is a little bit larger than the repulsive force, and the piece of paper is attracted to the rod. So that's how it works, okay? So we say that this field induces a dipole moment, and the energy is minus P dot E, and that's how you get this trapping force. Oops, because the force is the gradient of this energy, okay? All right, now, it's impossible to make an electric field in maximum region space without matter. And so, and the proof of that is simply because in the divergence of E in Maxwell's equations is equal to, the charge within this volume. But in vacuum, there is no charge, therefore that's zero. So the divergence of E means the field lines going in, field lines going out, in any volume have to equal sum to zero, the sum of the field lines going in and out. That's the theorem in static electricity. You can violate it with an oscillating electric field. So in an oscillating electric field, you just focus it, and there you have it, okay? So that's the basic idea. Fundamentally, it's something as I began to learn about this is my freshman physics saying, I want to really understand the intuitive level. And so this is what was happening at a very intuitive level. And then I was being told by John B. Orcombe, who would work with RAS, he said, and you know what, this dipole force changes sign when you go above and below resonance. And he thought that was really cool and said, why is that? And he looked at me and said solemnly, only Jim Gordon understands that. Truly. Jim Gordon, he has a Gordon and Ashkin paper, which Art said, no, I didn't have anything to do with the paper. He just put my name on it. But Jim Gordon did a really serious raising, lowering operator treatment of a two-level system. But it's not true. If you have a harmonic oscillator, so you have an electric field and you're oscillating the electric charge, okay? And so in this oscillating electric charge, there's a phase response. If you tune below the resonance, as the field goes up, the charge polarizes in step with the electric field, and it reverses and polarizes. So below the natural resonance of this oscillating this charge, it looks like DC fields, okay? And above it, there's a phase reversal. So it gets 180 degrees out of phase. And it's because of that that the sign reverses. So let me say it again. You got a particle, you make an electric field maximum by focusing the laser beam. The field is oscillating up and down. As the field oscillates up, okay, it goes like this, and this polarization is polarized according to the field. The field oscillates down, it goes like this. So it's in step. So it becomes static electricity again. And said, oh, now I understand it. It's freshman physics. It's a damped harmonic oscillator. Great. Okay, and this is what happens. And so, but Art was giving me all his reprints and trying to do this, and I was doing these calculations, and I decided, you know, Chuck Shanks shut it all down. He said, it's great stuff, but, you spent 8 years on it, and 8 years at Bell Labs is an eternity. 8 years is like inverse of your years to dog years, if you know what I mean. So anyway, then I was thinking around, noodling about this, but it doesn't look hopeless, and then sort of independently rediscovered this, which is. I'm not going to go through this. You guys know about, anyone here not know about Doppler cooling? Good. So I independently discovered this. I didn't read the Shallow-Hench paper, and it was good that I didn't for two reasons. Because in the Shallow-Hench paper, they said just surround the atoms with light using Doppler cooling, you can get it to cool down, okay? And so I just thought, hey, you know, in one dimension it works this way, and so how do you do 3 dimensions? We have 2 laser beams this way, 2 laser beams that way, 2 laser beams that way. I was describing it, and people said, you're at Bell Labs, you can afford 6 lasers. No, it's called beam splitters. But, but anyway, so we started doing this stuff, and I have to say that there's a few things I have to point out. First, by the time I had this idea, I went to Chuck Shank and I said, hey, this is so simple, it's going to work. And I did something else that wasn't done. And I said, you know, how long will these atoms hang around in this optical goo? So I was going to write a program and do it. But as I started to begin to code, after 1 minute, you know, like line 1, and I said, wait a minute, I've seen this problem before. It's called diffusion in a viscous medium. So it's Brownian motion. So what happens is you get jostled back and forth, and it's a viscous drag, and Einstein figured it out in 2005, says, oh, that's great. Just plug in the chemistry, and lo and behold, the atoms are going to hang around for like a second. But Ashkin was trying to trap the atoms for a millisecond. So I said to Chuck, this is so simple, it's going to work, and it's going to be even better than a trap. So he looks at me and says, okay, you earned the right to do this. You got positronium to work. No one thought that would work. Why not? Don't ask anyone else to help you. Okay, I promise. So anyway, meaning I could use my postdoc and I can enlist my postdoc and my technician, but I couldn't get John or Art to join. And so Why am I doing this? It's because, okay. So this is the apparatus. So I want to point out two things about this apparatus. The first thing about this apparatus is it was using a pulsed source of atoms. So I had a pulsed cheapo YAG laser that entered into the vacuum chamber that you see here. And the reason it looks pulsed is not because we have a really fast exposure time. The way you make these cameras is you take a picture of the apparatus and you turn off all the lights and you pass a card on the laser beams and you see the scattered light. And with a pulse laser, as you sweep the card, you see pulse, pulse, pulse. So what happens? The pulse hits a little pellet of sodium, evaporates it instantaneously, and you get a puff of sodium. And it comes into this vacuum chamber, these cross beams. Okay, so it used a pulse source. Why did I want a pulse source? I'll get to that. No, I'll tell you now. Because when I was a graduate student, I heard through the grapevine, because there was no published paper, that a graduate student at MIT by the name of Ray Weiss was assigned the idea of making an atomic fountain. You take a beam of atoms, you can go up like this, and his advisor, Zacharias, had this wonderful idea. You just send this beam of atoms up. Most of them just go, up and crash on the top of the vacuum chamber, but a very small fraction of them were in the slow Boltzmann tail. They would turn around and come back down. So as the atoms go up, they go into a microwave chamber. They're put into a Coriolan superposition. They go up, they come down, and it would be a much longer measurement time, okay? When Norman Ramsey, who's reminiscing about this, and he said, when Zacharias came up with the idea, I was completely scooped. It was such a great idea. Okay, so this graduate student couldn't see any atoms. And so he just, failed. And finally he discovered that the collision cross-section of the fast atoms going up knocked the slow atoms out of the way. So they never came down. Okay, and he just completely failed and had to, dropped out, but he managed, he finally got his PhD. His name's Ray Weiss. And his Nobel lecture, I read for the first time his trials and travails of this failed atomic fountain. So I did not want fast atoms knocking this stuff out of the way. So I was paranoid about that, but I knew that from graduate school, number one. Number two, I wanted a good vacuum because I didn't want fast atoms knocking anything out of the way for the same reason. So I got on a surplus list a old MBE machine that was going to go to universities, and Bell Labs, you can intercept and say, no, I've raised my hand, I said, I can get it. So we got this old surplus UHV chamber. But UHV, as you break vacuum and then you got to bake it and get down to a couple times 10 minus 10. It's going to take 3 or 4 days. And I said, I can't do this in 3 or 4 day turnaround time. So I put inside this vacuum chamber a copper manifold and it had liquid nitrogen. I painted it with Aquadag. This is graphite stuff. And so the whole inside of the chamber was a cryopump. And we could break vacuum late that night and early the next morning, early is like 9 or 10, it's back in the 10s, okay? But there were no, so we had fast turnaround time, but I didn't have to worry about atoms. And so this is what it looks like. This thing here is a little nozzle, so the infrared laser beam, or the green laser beam comes in here and strikes it, and out comes a puff of sodium. As I told you, this is the Zacharias fountain. Okay, so optical molasses worked. That was great. And then we set about trying to trap atoms. This is a picture of me when I was, I don't know, about 35. And Art Ashkin, and a picture of me, Art, and John. Okay. So we got this optical molasses. It's working great. And so we tried to trap atoms. So we tried the same thing that Ashkin tried, focus here, but now there's no, the original proposal, by the way, could not have worked because it's the same Zacharias bad experience. You try to trap a few atoms here, and there's a hole in the thing, and the atomic beam would just knock it out of the way. And so it was ingrained in me from the get-go. So I said, okay, that's not going to work. But once you have a good vacuum chamber, no fast atoms, pulse source, everything's going to work. And we couldn't get these large volume traps to work, which are analogous to the things he did in 1970, 1971. But at the end of this 1978 seminal paper, proposal for atom trapping, there's one paragraph. It says, finally, there's perhaps the conceptually simplest trap, a single highly focused Gaussian beam tuned well below resonance, such a TM00 beam has radially inward dipole forces as is discussed and a strong axial dipole force. So you focus so hard, you have this trap already, but it's so hard, the gradient along this direction overwhelms the scattering force that pushes it out. And you just got to tune far enough off resonance, okay? Now, why was this never considered? Well, in order to trap, even at optical molasses temperatures, which are like a fraction, 200 microkelvin, we thought. It wasn't gonna, how many atoms would there be in a density of ultra cold atoms? 1 million per square centimeter. The trapping volume is 10 to minus 1. So you would get 1/10 of an atom on average when you turn on the trap. I have a background of 1 million. Hopeless. So we just said, can't do that. That was rejected long ago. And then it was one of these things where it took a few days, maybe a week. And then what I found, and I said, there's something about a random walk. Oh, and there was one other trick. The trapping beams and the cooling beams were interfered with each other, but you just oscillate them back and forth. So if you look at the atom in a trap and you look at its natural oscillation trapping frequency, they're both on. That's a minor thing. But the major thing is 1/10 of an atom. But I said, well, look, I do another Brownian walk problem. And if it's near a trap, it gets in there, it falls down, it's trapped. And another one's trapped, and another one's trapped. How many would be trapped? A couple hundred, maybe 1,000 in a half a second due to a random walk loading. And so said, hey, that's pretty cool. Later on, I described it as sort of kind of like an analogy. You have some tavern Saturday night, people get drunk, and they wander around, and then what you find is you usually find these drunk people in the morning in a low potential well like a gutter. You don't find them in a high potential well, but they randomly walk around until they find a low potential well. I call it drunken sailor walk, and I got all sorts of angry messages, having no respect for members of the U.S. Navy. Okay. Now, this is now 1985. They said, we tried it, and it says, this might work. So then you say, this might work in the particles that Ashkin was trapping. Remember, he was trapping particles in water, and he was trapping, but he never tried a hard focus trap. And he was finding that in a hard focus in air, the particles get super hot. And so here we are making optical molasses and trying to trap atoms in a hard focus trap. And you could have trapped a particle water cooled in 1971. Was not done until 1986. And this is a picture of the thing he took. This is his first experiment. His laser dynamic water immersion. You have to get really hard focus. So he took a water immersion lens, and his hard focus, he could trap particles. And here he can lift particles off the surface. And he's looking with an Edmund scientific telescope and taking this. And you see the lensing effect. The light is coming in from the top, and it's going out with a slightly smaller divergence. So think of the momentum of the light of that beam, and this beam going like this. There's enough momentum to pull it back in. Great experiment. That took like a week. A week plus 16 years. And then the next one took about a month later. So off we were running, Optical trap. It's sad because Art really could have done this in 71. But so it was the optical molasses trap and optical trap and molasses and the optical trap in water. And so that was good. And then Ashkin found in the same year, they can not only trap particles, but he found, because it's in New Jersey, that stuff would grow in his samples, and like bacteria. And he found that he could trap E. coli and hold on to them and move around. And if you turn up the intensity with using a green laser, he would fry the E. coli. He called it opticution. And but if you turn it with an infrared beam, it would be gentle enough that you can actually have budding yeast. And then this is this paramecium crawling around the surface of this thing, and he would reach inside and use the optical trap to grab some organelle and just pull on it and then let go of it, and it would sort of semi-spring back, and this guy didn't seem to mind. Okay, so off and running. So at that point I said, look, we can trap atoms. Art can trap bacteria and organelles and stuff like that and live things. And so I said, I'm going to trap single molecules, but I had to wait until Stanford. But, so the next thing we did was the magneto-optic trap and a little bit of history. And so the question is, the dipole trap needed a very powerful off-resonant laser, whereas the scattering force was really a very effective force of pushing atoms. And so can you make a scattering force trap? And there's a theorem called the optical Earnshaw theorem, which says the answer is no. But the real reason it was a theorem, why it was called the optical Earnshaw theorem, if you have a scattering force that's proportional to the flux of photons, there's no optical sink or source, divergence is equal to 0, so it's the same as the other stuff. So light in, light out. Even though there were a few papers in the literature of trying to actually have schemes that had net light in, but it's divergence of something equals 0 is a very simple thing that you should understand. It's that the definition of divergence is literally flux lines in and flux lines out times the area. Okay, so that was that, and then along came this wonderful idea by Dave Pritchard and Carl Weinman. And they said, you know what? You can violate the Earnshaw theorem just as the optical trap and this dipole force violated, Maxwell's static equation by going to time oscillating fields. Dave Pritchard and Carl Weinman said, you can violate the scattering force, but it doesn't have to be proportional to the laser intensity. And in fact, they said in this wonderful article that it's possible to confine atoms with spontaneous light forces if you use something else like an external field, so that you make the beam this way and this beam asymmetric. So if the atom's over here and it moves over here, it would interact more with this beam because of some other energy level shift. And if it wanders over here, it would because of an energy level shift. And then you can do it if you can do it in all three directions, it would be great. And so they published this paper. And then John Dalibard, and they had some ways of proposing it. And Dalibard actually came up with a very, very clever way. And then the Dalibard solution I'm going to get to in a moment, but let me just, I want to show you a picture of John Dalibard. That's John Dalibard. I couldn't find a picture of him when he was the age where you were doing this stuff. Anyway, but so the idea is you create using some Helmholtz coils, but you wire them differently. So current goes around one way on top and goes around the other way in the bottom. And then you come in with circularly polarized light, and you just look in one dimension. And so these are the Zeeman level shifts, and this magnetic field is 0 at the center and increases linearly outward for small perturbations around 0. So if you tune, sigma minus light, which is in resonance with -1 to some excited state, and so that's in resonance. So if an atom's over here, it sees more scattering from sigma minus light, but if the atom is over here in the opposite direction in the magnetic field, it sees more from sigma plus light. So all of a sudden, you can get a simple scattering force, and it worked great. And in the bottom of our paper, we had a sentence. This is the Pritchard, Robb, Prentice, Al-Qaimon magnetization mine. We're extremely grateful to Jean Dalibard for giving us the seminal idea for the trap, because it was this magnetic field that he said, hey, because he was stimulated by the Weinman-Pritchard paper, he said, this is the way to do it. Pritchard said, great. So Davis at MIT, he assigns E.O. Robb to do this experiment. It doesn't work. They tried for about, I don't know, Davis here, maybe a year or so. It doesn't work. Okay. So in desperation, he says, okay, let's tell Steve CHU about this idea. Maybe he can get it to work. Okay, so Rob comes, and they set up in our lab, and we break the vacuum, we put in the coils, and everything's great. Of course, the obvious thing happened, we put in the coils wrong, and so that happens 50% of the time. You can think it through all you want, but it's 50% of the time it goes in wrong. And then I had to go off to Japan because I was doing an experiment with Alan Mills on the laser spectroscopy of muonium, mu plus E minus. And so I was left with, so Mara, Alex, and Rob were there, but Dave didn't come. And so Alex came in, his voice is trembling, he said, it works, it's unbelievable, it works. And so that's Jean Dalibard. And so in this back, that was his idea. So this was really a collective effort. Why didn't the experiment work at MIT? The pressure was too high. It was a sealed cell. So they didn't share my paranoia of a good vacuum. Okay, that paranoia stood me in good stead. So anyway, but it was everybody in the community helping in this one, that one. Anyway, so I moved to Stanford, and I'm 40 years old. Just in case you wonder what I look like when I was 40, that's me. We were all young ones. And so I want to talk about at the time I was doing the laser cooling trapping, I knew of one experiment that I knew I wanted to do, and that was to use cold atoms to measure time. And so the idea is that when atoms are there, they have energy levels, and if you can tune an oscillator to these energy levels, this natural atom energy level would provide the reference, and you tune your oscillator and you see what the frequency is. And so that's, and the great thing about this is the atoms are all of every element, same isotope, are all the same, and they're easy to isolate, okay? And there's another corollary to this, which people knew about. If you take a clock and bounce it against the wall, it doesn't keep good time. So what you want is you want the atoms not to be bouncing against walls. You can magic with Teflon coating things and hydrogen. There's a few magical things, but most of the time, no. Okay. So the really important big idea of doing this came from Norman Ramsey. And said, look, an atom passes through a microwave cavity, and typically in the transit time across the microwave cavity, you induce the transition from the ground to the excited state. And then you tune the oscillator, and that's great. But he had this stroke of genius realization that if you, as the atom goes through here, you put it in a superposition of ground and excited state, so it's both in the ground and excited state coherently. If it's in a coherent superposition, it's oscillating coherently, but it's drifting along in vacuum, and you put the other chamber like a couple meters away. And all of a sudden, you've increased the oscillation time from traversing a small microwave cavity. Higher frequency is good, but higher frequencies means smaller cavity, to small cavity 2 meters away. And suddenly, with this invention, atomic references became a time standard, okay? And then again, this is the Zacharias experiment. So when I got to Stanford, I said, I actually designed the apparatus when I was still at Bell Labs, and it was made at Bell Labs. Wasn't sure I was going to leave Bell at the time, but nevertheless. So it's a magneto-optic trap. We just trap them. We just push up the light. They go up. They turn around due to gravity, and we did this experiment. Okay. So then there are subsequent improvements in this so-called atomic fountain experiment. The basic idea was the Zacharias fountain experiment, except there were no hot atoms. They're all cold atoms. And so this went through a very rapid series of experiments from the first atomic fountain. Then the French got the first cesium fountain. And then I said, well, that's good, but can it really rival the best frequency standards maintained by the National Bureau of Standards around the world? And so what Kurt Gibble and I did was say, look, we're not microwave experts, but Hewlett Packard's down the street, and they were making cesium atomic clocks. They're this big, beautifully engineered, chamber here, the whole thing's in vacuum. And so I said, can you give us one of these little microwave gizmos, okay? And sure. So we just turned it on its side, turned it upside like this, put it in the vacuum chamber, shot it up, and came down. And then we showed that it was the first accurate, the short-term stability began to exceed the National Bureau of Standards short-term stability. And then finally, it has to be an absolute measurement, just not a precise measurement. And then the French came back with an accurate clock. Now, a lot of water was passed under the bridge. And now with long measured times of very narrow-tuned resonances, very sharp resonances in strontium, for example, Jun Yi and his colleagues holding them up in a lattice are getting ridiculous things. That's not 10^-18, that's a misprint. This is an old slide. What they really are, it's, if you started a clock like this when the universe was born 13, 15 billion years ago, it would be less than a second, but they've done better than that. These are history of microwave times, that's due to Norman Ramsey. Then optical fountains and things like that, and this is the latest Jun thing down here. It's truly ridiculous. So if you started one of these clocks when the universe was born, you would know what time it is to better than a millisecond. And you might say, isn't that overkill? Aren't you just showing off? And the answer is yes. Not really. The very best measurements in physics are frequency measurements because you're just counting. And the standard of a frequency measurement is the time standard. This is not yet the time standard, but it's leading to all sorts of great experiments, okay? All right, so now I'm at Stanford. The fountain works, and the first reports, we had large error bars. We reported 240 microkelvin, which is at the minimum, but big error bars. And then Carl Wyman did it with cesium Boulder. He got roughly the same. And then Bill Phillips's group said, well, there's something, maybe not. So one of his postdocs said, we'll do another experiment. You just, we just turned off the light. They flew out and then recaptured the slow ones. So they said, we'll do a little better. We'll just turn off the light and let's just watch them drop and then watch them spread. And what they found was that the temperature was not 240. It was actually 40 microkelvin. And if I look back at the data, it was there. We blew it. I blew it. Completely blew it. Anyway, never mind. But this was amazing because this was below what we thought the theoretical minimum was because it was a two-level system. And so this is what we call a strong violation of Murphy's law. It was working better than you expected. And physicists are always geared to think of reasons why it didn't work as well as expected. Okay, and so then the theory was developed. This was discovered in the spring of 1988, and the theory was developed in the summer of 1988. And it was developed by Claude Contanucci and Jean Dalibard, independent with me. Let me just tell you fundamentally how it works. When you come in with polarizations, the optical molasses, the canonical one, whenever it is polarization this way, polarization this way, and polarization. So the three orthogonal polarizations. And I remember Claude Contanucci and I were at a conference, a low temperature conference, not those medium temperatures of liquid helium. That was low temperature in those days. And we talked after, we talked at lunch and said, we don't know what this is. He said, I didn't know what this is. But we decided it can't be a two-level atom, it had to be multiple levels. We also said, look, you're getting roughly the same thing in cesium and sodium, but the hyperfine levels are really different, 9.1 gigahertz, 0.7 gigahertz. So it's got to be a Zeeman sublevel. And so what was it due to? It had to be optical pumping. Didn't know. He went back to Paris. I went to Ted Hensher, was visiting him. I said, yeah, it's optical pumping. He said, well, okay, maybe you can figure it out. Why don't you don't do it, and just spend some time in the library. So I spent a lot of time in the library reading about optical pumping. And it was like optical pumping is like invented by Kessler and others. And there are things called Contanucci states. So I was getting really depressed. So I think they're going to figure it out before me. And then something happened. It was at another conference. And someone said something magically. He said, when an atom is oscillating like this, it polarizes the atom so it goes like this. Okay? And so I said, wow, that's true. If an oscillating field, it goes like this, right? What about circular polarization? So it's going like this. So it wants to make it go like this. And so it optically pumps the atom into a Zeeman level, plus or minus. Or in linear, it mostly optically pumps in the center. But it changes polarization. So I said, because of that, if you go, and we knew that the polarization was short. So if it's in here, it's in a low state. And so, so I call this polarization gradient cooling, and I had a heuristic argument about how they would torque the thing. And meanwhile, Jean Dalibard and Claude Konrad had a very simple, fictitious 2 levels in the ground state, 4 levels in the excited state. And what happens if you're over here, for example, you have circularly polarized light, and the atom optically pumps into this state. Remember, the atom's spending most of its time in the ground state, only a very small fraction of the time in the excited state. And we also know that when you have optical light on the system, you have what are called AC star shifts, light shifts. And the light shift is proportional to how strongly coupled the atom is. And when you have circular polarization going around, and you have the electron circular polarization going around, it's most strongly coupled. And that's the polarization like this way or this way in my simple quasi-mechanical thing, quantum mechanically comes out, right? And so this means when it's here, it gets into this state, but this is the lowest energy state. And when it moves over to this region, it says, ooh, this is now a high energy state. So it's like it's climbing up a hill. And what the French did, they called this Sisyphus cooling, okay? Because it's like this, in Greek mythology, this person, he's condemned to roll a boulder up to the top of the hill, gets near the top of the hill, and someone puts him down at the bottom again. So you're at the bottom of the hill, you're climbing up to the top of the hill, but you have optically pumped in low energy state. Now you're in a high energy state, but while you're climbing up the hill, you're optically pumping back to the low energy state, and you go through this, okay? And it's true in this semi-classical of torques, of turning the atoms. Okay, so that was, so I got to Paris. Dave Wine was in the audience at this conference, and he said, what happened? You were paying attention to all the talks, and your head went down, and it never surfaced. I said, I figured it out. So I got to Paris in the atomic physics conference, met Jean Dalibard, and said, he's got a big smile. He says, hey, Steve, I figured it out. I said, I did too. He says, so John says, what did you do? He says, this is how it works. He says, yes, that's how it works. It was very cool. Anyway, and this is Sisyphus climbing up a hill. So, okay, so optical molasses, and the real optical molasses with multi-level atoms is the mainstay in cooling. But I just also should mention, although it's not, there are dozens of cooling methods, by the way, maybe several dozen. But the best ones are the ones that cool to very low temperatures and very high phase space density. And the polarization gradient, or Sisyphus cooling, is the workhorse, that in a mod. But I should mention this. This is due to Vladimir Vulatek with Andrew Kerman and Qing Chen, who's a fellow at MIT, and Qing Chen's University of Chicago, when they were in my group. And what they said is you can take vibrational levels of an atom, and you look at the vibrational states, and you do a Raman transition that oscillates between these magnetic sublevels. Anyway, I'm not going to explain this because I want to get to more cooler stuff. So this is very cool. It's very cool because you can get really high phase space density and cold temperatures with this. Because once you cool the vibrational levels, they enter into a dark state. And after you do it, so they stop scattering photons. And that's a really important thing. And so it's not, I don't know why it's not more widely used, but this is, you know, the really good high phase space density cooling, which is what we care about. Okay, so lots of cooling, trapping, you know, there's magnetic trapping. Bill Phillips did the first magnetic trap. Great stuff, using a Zeeman slower. When I started this, the optical molasses experiment took 10 months from the time of the idea from the time I started writing the draft. And we didn't have a vacuum chamber. So that's why I made dog years and people years. And you can go pretty fast if you have a really good technician and a really good postdoc. My technician was Alex Cable, who founded and owns all of Thor Labs. And the postdoc was all of it. There's no venture capital in this. And Leo Holberg is a professor at Stanford now. Anyway, so that worked. What are the applications of laser cooling and trapping? Well, the most important application is this, right? But in all honesty, there were other things. And so, it led, for example, to boson condensation, led to a Nobel Prize with Kenan, Carl Wyman, Eric Cornell. It led to, quantum entangled states and quantum computers. And I became convinced the best shot at a real quantum error-correcting quantum computer are neutral atoms held in dipole traps. So, and I got a good dose of that, and I'm getting pretty convinced of that. General tests of parity, non-convergent timing, all this stuff, okay? Okay, so now, this list did not exist when I was doing laser cooling and trapping. All I knew about clocks. Because I was only focused on making it work, just like positronium. But a miraculous thing happened after we got it to work. And all of a sudden, ideas started coming like crazy. Because once you accept the reality of it, it's a different world. So this is what happened to me. This is what happened to people in the field in general. Okay, so now let's go continue in this saga and we'll talk about atom interferometers. So we know from de Broglie and onward that atoms have a wave-like character, quantum mechanical wave-like character. And you can do an equivalent of this if you take a very well collimated beam and single slit diffraction. So it's just like what Young did with an incoherent light source and a little slit. You make something and a double slit, and Jürgen Mlinek showed that you can get interference fringes, okay? So the double slit experiment is okay, that's great. And then the first atom interferometer was done by Dave Pritchard, so he was thinking, okay, you have a very well collimated beam, so the temperature in that direction is really cold. So the de Broglie wavelength, the effective de Broglie wavelength along this direction is big. And so then you have a diffraction gradient and you do this. But he decided to kind of invert it. So instead of using light and matter to make a diffraction gradient, why not use atoms and light to make the gradient? So using a standing wave of light with the optical dipole force, he showed that you can diffract atoms and sort fringes, okay? So that was done in 1991. And then 3 months later, after that, these two experiments were published, and then 3 months later, we reported our interferometer, which was very, very different. And it was based on the following. Here you have an atom, and you have a ground state, two ground states. And if you made a virtual transition, one photon goes up and make a transition, a virtual transition, goes up and comes back down. So the virtual transition up is induced by this atom. The atom gets a little momentum kick. Okay, so this going up makes this momentum kick, but this beam stimulates the atom back down. So an atom goes from here, gets a kick to the left. The other one stimulates down, but it gets another kick. So then all of a sudden, by putting the atom into a superposition of these two hyperfine states, you can use the momentum of the light to actually induce the transition, okay? And that's the idea. So now it's in a coherent superposition of ground and excited states. It's exactly Norman Ramsey's trick. It was just one step away. Norman Ramsey had a big influence on me from a long way. He had a big influence on all atomic physics, to be quite candid. But anyway, so over here, so this part of the atom is traveling along the original way. And then over here, you can induce, and then this one can go up, this one can induce, there's part of the atom goes up here, part of the atom goes here. but it's only the parts of the atom that combine together that interfere. So I'm not showing those other paths. And so Mark Kazovich and I did this, and once we had the atomic fountain, this experiment actually took less than a year, right? Because we had everything. And all we had to do is introduce 2 beams, pulse, pulse, pulse. And so in our first paper, we got a part per million precision in the interferometry. Why was it so accurate? It's because in this laser transition up and down, you're tuned off the resonance. And so the lasers are bobbling up and down. But we're making these 2 laser beams through an electro-optic modulator. So if the laser frequency bobbles up and down, the difference frequency is spot on. It's defined by a microwave oscillator. Okay? And the momentum, the fraction of the momentum of bobbling up and down is part of a million. It doesn't matter. So we had automatic clock accuracy from this very simple idea because it was a Ramsey clock in the end. And so for that reason, so in 91, we got a part in 10 to the 6. In 92, we got a part in 10 to the 8. Okay? Now they're a part in 10 to the 14. Something crazy. And in 99, this was significant because we decided in the first equivalence principle, we dropped the corner cube at the same way we dropped atoms. And we showed that the corner cube, the macroscopic thing, and the atoms have the same. So it's off and running. And so again, it's a very simple idea of replaying back someone else did this, and so we did this. And as I said before, now people are thinking of dropping strontium atoms because it has this narrow, exquisite line in an optical fountain, but then they're scaling up. So Mark started working on a 5-meter fountain, a couple stories, and then his graduate students started working on another 5-meter, but now with strontium, and then Fermilab, because they said, oh, this is a big project, we can get a lot of money from the government. So they're going to drop strontium over 50 meters. Okay. And it's going to be very good tests of the fundamental physics. Okay. All right. So I get to Stanford. I get an MD PhD student to teach me a little biochemistry so I can glue polystyrene spheres onto DNA. In those days, you had to, and so he said, oh, use the avidin and biotin thing, it's good glue, but we had to learn how to biotinylate the DNA, and then we had to learn how to put avidin and all this other stuff. And I was moonlighting, so this MD PhD student who was working with Jim Sputich, he didn't tell Jim that he was spending 4 or 5 hours each night working with me. And so then he would get up the next morning, and so he was going on 5 hours sleep for a better part of a year. And so Steve Krohn and I figured out how to hold on to this. We published a little abstract journal in 1991. Okay, and I didn't publish any archival thing for a while. And Jim, then I started helping Jim Sputich with optical tweezers, actin myosin. So the first actin myosin papers were done in barium. But so Jim Sputich asked, Steve, what about this? You're going around the world talking about this. You should publish it before you get scooped. And I said, well, it's not working all the time. It worked when I was doing it, but I handed off some grads, it's not working. He said, how many times what fraction of time does it work? Half the time. How many times? Dozens. You haven't published that? So anyway, and I couldn't help them. I didn't know anything about offers. So finally, we were doing this stuff. So that's Steve Krohn. Steve Quake got his undergraduate honors thesis with me on optical tweezing of DNA. This is we hooked up a laser beam to a tilting mirror and put it on a joystick. We put dyes on the DNA and we started squirreling around. And there's a background of unstained DNA, and so it looks a little weird like this. But it was, and they were doing this got it to work, and for a couple of days they were just in the room going like this, watching. And I said, okay, we're having lots of fun, but we got to do some science. Okay, so what science can be done? Okay, so there's a theory. I didn't know anything about polymers. So the first thing is stretched out and just relaxed back like a rubber band. I said, hey, that's cool. Why does it do that? And then I said, it's because when you stretch out, it's a very unusual state, and it just wants to go into a crumpled mess because there are many more crumpled messes than there are stretched states. So it's just entropy, okay? And so that's cool. And so I said, this is in the early 90s. Then Eugene gets his Nobel Prize, I think in 92. And he has a big smiley face and École Normale. And he works the right word, reptation, on the blackboard. And so what is reptation? So during this time, and there was a big intellectual effort that really started really with the observation of lamp shift and quantum electrodynamics. And so in this, at a high level, it's universal, these field theories, you have very high frequency events that could affect the energy of the hydrogen atom, the lamp shift, or the charge of the electron. But people figured out how to self-consistently do this and renormalize it to give you predictions at lower energy states. Okay, if you just finally adopt the idea that the electron has an electron, but you renormalize once, and that same correction can apply to everything else. So those fundamental ideas that were applied in field theory, in high energy physics, that were then atomic physics, were first done by Phil Anderson, then generalized by Ken Wilson, to use renormalization group theory in condensed matter systems, including polymers. And de Gennes especially wrote this thing as scaling concepts of polymers, have used renormalization group to understand polymers. But what it really is, if you cut down to it, is it's a mean field theory that said these polymers are very, very complicated, long squiggly molecules and so how do you get these dynamics of long squiggly molecules into something simple? And so de Gennes says, if you consider a single polymer, the red one, but it's all entangled with all these other things, and you imagine these other entanglements, but now orders of magnitude more than what you see in this cartoon, what he said is, this polymer is defined in a tube. And in this tube, it can't go orthogonal to the tube. The only way it can diffuse into a new area is by snaking through into a new thing. So he called it reptation for snakes. And he was trying to explain viscoelasticity. If you have a polymer soup in a short time scale, there's no, you're squishing all these polymers and it looks elastic. But if you let it go on a long time scale, these polymers ooze around through the tubes and it becomes viscous, okay? And so we did this and we drew an R and let the R relax. And this is what it looked like. So this is in this soup of other DNA molecules. And there we got 2 beads, so I wanted, we only want 1 bead, so I put that there. And there you go. And what you're going to do is trace out this really complex pattern. And you notice entropic elasticity is making it retract, but it only retracts where it is on the tube. So as a graphic in your face, reptation is in a tube, and it's even better than that because if you look very carefully, you begin to see the tube starting to wiggle. And so second order effects of the tube relaxation. Okay, but this was very different than the usual polymer physics to use neutron diffraction or stuff like that. It's just right out there. And so very, very cool. We did an elongation experiment where we had fluid going this way and fluid going that way. And you look in this observation region. So this is called elongational flow. So it squishes the polymer in this direction, tries to stretch out in that direction. And what we did is we found that different polymers were stretched differently. And these are some cartoons of how these polymers stretched in this elongation flow. And we found that we didn't call it this. We found that if you start this polymer, they would unfold very differently. And so de Gennes we submitted this to Science. It got published. He wrote a commentary. He didn't like the idea. He said, this is crazy. You know, there's got to be some experimental artifact, but it's a simple polymer. And how could a simple molecular polymer act as an individual? He says he can't. So there's no molecular individualism. And, you know, we said, well, there are individuals. There's me and my two brothers. And Nobel Prize, okay, we're individuals, a lot of degrees of freedom, very complex, but polymers aren't. And so, but it was true, and it's a simple model of why it is. But then we went through the changes of any new scientific discovery, okay? First, they tell you it's wrong. Then they understand what you're saying, and they get it, and they say, ah, yes, now I understand it. It's trivial. And then finally, they say, you weren't the first to think of this. This happens every time. And so why was it acting as individuals? Because the starting point wasn't exactly the same. The starting point was random starting points due to Brownian motion. And so if you take this elongation, just stretch it, you can do a thing and you could stretch this way. And once it stretches into a loop that way, it's kind of trapped and it takes a long time to unwind. You can do it, turn it 90 degrees to stretch it this way, it unwinds much faster in bunches. So we just actually did some simulations of how you stretch these things, and it followed what we saw. And it was trivial. So anyway, so, okay. So we found that by looking at these molecules, these polymers, we found that they actually, even placed in what are called identical situations because of the random noise of the environment, they could look like they're individuals, so this molecular individualism. And so I said, okay, what about biology? This is polymers. Biology is much more complicated. Of course, you find it harder. And suppose you're an alien with a telescope and you measure the average properties of, let's say, the people in this room, the people in Boston, people on the Earth. But you can measure certain properties with high accuracy, but there's billions of people. And you find an average, each person has one testicle and one ovary. But if you measure them individually, you find out that's not the real distribution. And so I said, hey, this is really going to be cool. You can measure this stuff, and you can really find out stuff. And it really changed. And so this started happening in the middle 90s. The first ones were optical tweezer experiments. That was single molecule experiments. But later, single molecule FRET. Single molecule FRET was invented by a professor in the biochemistry department at Stanford, Lubert Stryer. FRET is you got a green molecule and a red molecule, and you excite the green molecule. But if they're close together, this oscillating green molecule has a near field thing that gets the oscillating red molecule to oscillate. Coupled oscillators. It's not photons, it's coupled oscillators. But this green molecule oscillates the red molecule, but then once the red molecule is excited, there's a probability there'll be a photon thing, and it doesn't transfer the energy back. So if they're close together, green to red is 100% efficient. If they're far apart, the field isn't that, so that it doesn't change, okay? So then Daniel Shimla, Shimon Weiss, and Tagji Kar was a graduate student, demonstrated single molecule FRET, and they drifted in a confocal volume, and they said they put a molecule and two dyes, and they said, hey, there's fluctuations here. And they were good about it and said, well, these fluctuations cannot be, but they can only see the molecule drift in and out with a very short fraction of the time. Of course, what they wanted to do is put it on a surface and look at it there. They tried that, but they're good enough scientists and realized that the molecule just died on the surface. It stuck to the surface and it was longer. And so Tagji Pa joined my group. He was very discouraged. He said, I don't think FRET has a future, single molecule FRET. He says, no. We're going to tweak it. So how are you going to tweak it? We're going to cheat. How do you cheat? You have a surface. And if you have something like a nucleic acid that's negatively charged, DNA is negatively charged, RNA is negatively charged, the surfaces are negatively charged. So you tether this molecule to the surface. In the standard buffer salt solutions of life, The bi-screening length is 1 nanometer. So you got a couple of nanometer tether. So it's up there and thinks it's happy in some nice environmental, biological environment. If it happens to go near a surface, it just bounces back because it sees a repulsion. So the first experiments we did, we cheated, and we just used nucleic acids which were charged. And all of a sudden, you know, on a surface, we can do all this stuff. It's great, and we're off to the races. And that's all it was. And then a year or two later, Tajib says, okay, I want to go back to proteins, how do proteins interact with DNA and stuff like that. You know, 2 weeks, 3 weeks pass. He's looking really discouraged and saying, it's not working. Just like it did in Berkeley, it's not working. So it's not, we can do nucleic and we can look at RNA enzymes, fold and unfold, and we were doing that, but we couldn't do, if you can't do proteins, you're leaving most of biology out. And so it didn't work. So I was looking at it, says, okay, Tajib, don't get discouraged. Walk with me. Just walk across the street to the chemistry department. And he asked the chemist, hey, we got this sticking problem. What do you suggest? Talk to Harvard McConnell, Steve Boxer. Suggested 2 things, polyethylene glycol and lipid layers. Polyethylene glycol was shown to work peg on gold, and both worked, but the polyethylene glycol worked best. Okay, so anyway, so all of a sudden biology was doing it, you know, biology's thing. And so the only trouble with this is, you know, I'm no longer young. And so this is a Gary Larson cartoon. High above the hushed crowd, Rex tried to remain focused. Still, he couldn't shake one nagging thought. He was an old dog, and this is a new trick. So I was starting to learn biology. And anyway, so I'm going to stop with just one last thing. And I'm beginning to find this out in the biological experiments. And it was stimulated by something I read when I was young, Irvin Schrödinger, who said, from what we've learned about the structure, this is, you know, what is life? What we learned about the structure of living matter, we was prepared to find it working in a manner that cannot be reduced to the ordinary physics, not because there's any new force, but because the construction is different from anything we yet tested in the physical laboratory. And if you went to my lecture yesterday, these molecular motors are very, very sophisticated and they work very well. But the take-home message is we made machines by eliminating friction, okay? And in life, at a molecular scale, you can't eliminate friction. It's embedded in a viscous fluid. It's overdamped. And the thermal fluctuations are huge. So if Newton were the size of an E. coli, his laws of motion would be different. An object in motion typically stops, but there's an unseen hand of God jiggling around, and the force is proportional to velocity, okay? And yet, these machines work very well, and they actually use in a very clever way statistical fluctuations, which was unlike we ever thought before, but then you say, holy smokes, this molecule is really smart, or someone who made the molecule is really smart. Okay. So with that, one last little bit. It was mentioned I got sucked into being director of LBNL. I never wanted to be a bureaucrat. But I was starting to give talks about energy and climate, and I realized when I was a graduate student and a postdoc there, I was also an LBL member, and 16 times working at LBL, I got Nobel Prizes. Probably 36 by now have gotten Nobel Prizes who trained there as a young scientist, a graduate student, a postdoc who started their career. So I said, if I can get these guys to think about energy, it would be great. And so that's what I did, thinking I'd step down after 5 or 6 years. And then unfortunately, President-elect Obama asked me to do this other thing. And so I did this other thing. The Gulf of Mexico, final story, how did it happen? So I had suggested to the BP, you know, the blowout prevention pump was just gushing all this oil and gas, and they didn't know the state of the valves. It says that, you know, if you do take a cobalt-60 source and just, you know, do like a dental x-ray, it can go through a couple inches of steel, right? So I said, maybe you can look and find out where the valves are doing. And I told this to the BP guys. They laughed at it. Says, yeah, radioactivity. You know, this guy's from LBNL. That's where the Hulk got made. And it's just, and then the next day or two, so the story goes. I said, maybe he's right. And then they found it's actually commercially available. So somehow the president hears about this. So at the end of April, you know, it's late April, after cabinet meeting, he goes up to me and says, CHU, go down there and help them stop the leak. Yes, Mr. President. Not forming committee, just, you know, you're a practicing scientist, help them stop the leak. So I thought, okay, what do I do? There are a couple out-of-the-box crazy thinkers who are quick learners and are willing to, you know, I wouldn't want to collect petroleum engineers. BP had a lot of them. The industry had a lot. So, you know, guys, one or two people from Jason, Dick Arwin was, Dick Arwin, yeah, he's brilliant. Fermi said he's the smartest person. Fermi said Dick Arwin's the smartest person he ever met. He said, I know about it, but, you know, he's like in his 80s. You know, he's still okay. And he said, he's still okay. And boy, is he still okay. He's in his 90s and he's still okay. And so these people, we showed them, and so I called them all up. I said, you know, I want you to give me advice and have this, we want to help BP. I said, I don't know anything about oil, but we're going to learn what the hell. And he said, okay. And they said, okay, you know. And so, by the way, you know, I got to ask my wife if it's okay. I got to ask my department head, and got to start teaching. So, and say, oh, by the way, tomorrow morning at 8 a.m. in Houston, the whales showed up. I spent half my time for 2 months down there, and the others would fly in and out. We were in constant email thing, and then after we saw BP in action, I said, these guys do need our help, and we really did help them stop the leak. We didn't talk to the press at all. I said, we're not there to talk to the press. We're helping them just stop the leak, and we helped them stop the leak. And it was thrilling because the cabinet member said, Steve, how can, you know, this is really stressful. You look happy. I said, yeah, I'm solving a scientific problem. I was in hog heaven. I get to do research again. But it's all physics, actually. So it was fun. Fukushima was also not as much fun. It was a little depressing. But anyway, I better stop. Thank you. That's the end. When I came back, I didn't want to be a continuing bureaucrat. So I wondered whether I had any, you know, when you're a bureaucrat for 10 years, there's this silent sucking sound that drains the lifeblood out of you. And I just wanted to know if I could have new ideas. So
maybe you can take a couple of questions from the audience, if there's any. No questions.
No questions.
Well, there's one in the back. Okay.
Okay, start it off.
So I really appreciate that you were a scientist and the Secretary of Energy. I think that's excellent. Based
on your experience, do you think it is a good idea for other administrations, regardless of political party, to recruit technical experts to lead administrative organizations, or should they, you know, have managers that don't necessarily have technical expertise but are good at just managing?
Well, I think you need both. You need to be a good manager, but if you're a good manager and you're a scientist and then a former a scientist and not an active scientist, you actually think of the world differently. And so Obama was very unusual. I didn't do politics. They weren't even sure I was Republican or Democrat. And so President-elect says, everybody's telling me you should be the Secretary of Energy. We talked for an hour, just the two of us. And he wanted to know what I thought about this, that, and the other thing. And I also, you know, was wondering what he was like. And after this hour-long discussion, I came out, it's in Chicago, called my wife, this guy's really good. If he asks me, I'll say yes. But one of the things I did say in that is, I know in Washington, D.C., there's a lot of political appointments. The secretary, the deputy secretary, the undersecretary, all, you know, like 100 political appointments. I said, I want to hire who I want to hire. You're welcome to make suggestions, but I want final say. And he said yes, and he kept his word. And so when I got to the Department of Energy, I got on the phone and started calling people who I liked, friends, really aces. And I started calling them up myself, and we get and then we get a few, and then they and I call up others, and we started recruiting unbelievable people. 6 members of the National Academy of Engineering and Science, a couple of them elected in their early 40s, but they were still in their mid 40s, at 44. Can you imagine working in the US government when you're 44 or 45 and you just got elected in the National Academy of Engineering? No way. But these guys were coming. And it was magic. Working 60, 70 hours a week, and it was a snowball effect. And so now these people since have left, but they're, one's the dean of the new school at Stanford. The first dozen people at Breakthrough Energy Branches were all from the Department of Energy. There are people all over, scattered all over everywhere, who are now leaders or giving out funds or, starting companies. And it was, and it was not only magic in getting good people, but we all became best friends, which is also magical. And we still stay in touch. And so you think about that, okay, Obama, I was the first scientist cabinet member in the history of the United States. Okay, and I was a practicing scientist. And do I think? Yes, because when I was down there in BP, I was saying, you better listen to me, because BP would, it was like to call up the President of the United States. And they did some really stupid things. I said, no. And so, and then you're at cabinet meetings, and you're in the security room, and you're down in there at the big boys and big girls tables, right? You're not, and so it is really important. Having said that, most political people do not like scientists and engineers because they are swayed by facts, and they tend to want to answer questions. And then when political forces want to do something that is against the science or counter the science, they're not going to listen to you. Now, Obama had my back, so I could ignore some of the other people in the White House because he liked me, he trusted me, so I was protected. And so you need a president who's willing to do that as well. So I didn't realize how unusual he was until, then I saw Trump. Completely alternate universe. But Joe Biden's more of the same. He's a nice guy, he's great, but it's very, he didn't appoint any scientists.
Maybe on this note, since it's also getting quite late, I'd like to thank our speaker for a wonderful